Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 18 in our incredible new tutorial series where you're going to learn Fusion 360 or you're going to die trying. What I'm going to need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to you guys who are helping me out over at Patreon. It is your support and your encouragement that keeps this great content coming. You guys that are not helping out yet, take a look down in the description. There is a link over to my Patreon account. Think about hopping on over there and hooking a brother up. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And we're continuing today on this concept that we've been developing over the last few lessons of design rules. When you design, you should not be designing by thinking of, I want a picture of this object. You should be designing with your manufacturing capability in mind, and you should be designing to the manufacturing capability that you are going to be using to actually create the object that you are drawing. It seems like most of the educational material that I see on YouTube related to Fusion 360, it is being treated more like it is an arts and crafts project where you're creating artwork as opposed to a tool to allow you to create real world physical products, prototypes, projects, things like that. And so this is that concept of design rule where you are designing with your manufacturing capability in mind. And I introduced a new word in today's lesson. I call it metrology and design rules for 3D printing. Design rules are the rules that you follow when you're designing so that what you design will be able to be effectively manufactured. Metrology is after you have made your object, you come in and you make measurements. Metrology is the art and the science and the engineering associated with making accurate measurements of the object that you are making. Hopefully that makes sense. And so what we are going to do is we are going to kind of jump into this topic. And I'll just remind you that in last week's lesson, we did create this design. And the purpose of this design was to allow us to understand the manufacturing capability of our printer, the precision with which we can define various types of features in our Fusion 360 designs. And then we did, in fact, go in and we printed that out to create this physical object. So what we are going to do today is we are going to take our calipers and take our design rule features that we printed, and we're going to now come up with a list of our design rules. But before we just jump in and start doing that, we got to kind of ask ourselves, what is it that we want to measure? What are the things that we want to understand when I'm designing? What are the things that I should be thinking about when I am designing? And so what I did was I started by creating a preliminary list that I called my Creality Ender Design Rules. And these are the things that I want to go back and determine from that design rule checker that we printed in last week's lesson. One thing I want to know is, what is my x-axis precision? How precisely can I define mechanical objects on my 3D printer in the x-axis? Then similarly, y-axis precision. You don't necessarily expect those two to be the same because we have one motor and one belt and one set of rollers for the x-axis, and we have another motor, another belt, and another set of rollers in the y-axis. So we don't necessarily just assume that our precision in x and our precision in y will be the same. And certainly our z-axis precision is a completely different axis that is even mechanically behaving differently, so we would really expect z could be different than x and y. Another thing when I am designing, I need to know what is the minimum line size that I can print. What is the minimum feature that I can print? That if I try to print something smaller than the minimum feature, I end up with nothing. What is the minimum feature size that I can print? Now, very closely related to that is what is the smallest gap size that I can define? So imagine that I have a line here and a line here and a gap between them, and I make the gap smaller and smaller and smaller. How small can I make that gap until I no longer have two lines, but those two lines have blurred into each other, and I no longer have two lines, but I have one line. So I need to understand what is my minimum line width that I can print, and what is the minimum space between lines that I can have. Then similarly, what you can see is that so far I've been talking about kind of like straight lines, things like rectangles or squares, things like that. But just because I can draw a straight line doesn't mean that if I draw curved lines that they are going to behave exactly the same. And so I create this idea of not just x-axis precision, but what precision do I have when I am creating something or designing something that is not a straight line. So I call that a cylindrical peg precision. So I design a peg and I have that peg designed to a certain diameter. What diameter do I actually get? What is my cylindrical peg precision? And then you got to think a peg is different than a hole. I might be able to make a peg very accurately, but a cylindrical hole, how precisely can I define that? So we've got the design rules of cylindrical peg precision and cylindrical hole precision. Now, if you put a hole on a peg, you have something like a gear or a wheel on an axle. We need to understand what tolerance we need to use for those types of rubbing, moving joints. That if I make the hole exactly the same size as the peg, you can imagine it's very likely that that isn't going to work very well. So I need to include some tolerance. For my printer, what is that tolerance? The tolerance for making a cylindrical axle type joint. Now an axle type joint, you want it to be where there's not wobble and there is not a lot of play, but you want it to be very smooth in its motion. You don't want to feel a lot of drag or a lot of friction. But then there's other types of rubbing joints where you want that friction. Like remember our eyeglass holder where we put the top on our eyeglass holder? We wanted it to snugly fit in place, but be able to take the lid off or on. I'm going to call that a snug slip fit. A slip fit that is designed to be used multiple times. I slip it on, it stays on snugly. I take it off, I can put it back on, it stays on snugly. I need to understand for that type of joint, what is my tolerance? Then I have what is called a tolerance for a compression fit. Like imagine I have two holes and I have two pins and a lid, and the idea is I want to compression fit those pins in those holes where I want it to be like a permanent type of thing. I would press it in. It's going to be hard to get in. It's going to go in once, but once it goes in once, it is in there. It wouldn't be something you would be taking on and off. It would be something that you would do one time during assembly, and I call that the tolerance for a compression fit. And then another very important design rule for a 3D printer is you can't just print onto you can't 3D print over air. That 3D prints like to have underlying layers that you are designing on top of. And so there's the kind of idea of how large of a gap of air can you print over before the filament just goes down and starts making spaghetti? So like, can you print over a millimeter air gap, 5 millimeters, 10 millimeters? How large of a gap can you have in your Fusion 360 designs and still be able to print over it? Does that make sense? Okay, guys, leave me a comment. Does it make sense what I'm trying to do here? Are there things that I'm overlooking that you had on your list when you did the homework? Are there things that were on your list that I didn't put on this that I need to kind of add more design rules? Maybe there's things that we would be designing that I'm not anticipating. So leave me your feedback down below, either in the live chat or if you're watching this later in the comments, because we're going to start with these as our design rules. But as we start doing more and more complex designs, we're probably going to come in here and start doing, add more things to the list. Okay, so what I'm going to start with is I just really want to kind of start with the x-axis precision and the y-axis precision. And I think the easiest way to do that were with these very simple little cube structures. And so I'm going to come in, I'm going to get my calipers, I'm going to turn them on. And then do you guys think I should zoom in maybe a little bit here? Let's see if I can zoom in a little bit more. Okay, I think that might be good. So I'm going to come in, I'm going to zero this out, and then remember we designed this to be 25 millimeters by 25 millimeters by 25 millimeters. I'm going to come in, I'm going to get this, I'm going to come in, and then I'm going to make a measurement. And you can see that that is 25. I wanted it 25 millimeters. It is 25.04. That is really pretty amazing. That is pretty amazing. And that is right at 25. I'm going to come in here. I'm just trying to kind of look around. 25.04. I'm just looking at different areas. 25.04. And so what I'm going to say, just looking along the x-axis, what I'm going to say is my x-axis precision is going to be, I'm going to call it 0.05. I just had to look at it. It's kind of amazing that it's really that accurate, 0.05 millimeters. So I am designing to a precision of better than 1/10 of a millimeter. I'm manufacturing to a precision of better than 1/10 of a millimeter. Let's come back over and let's look at that in the y direction. And so I'm going to come in, I'm going to look at this along the y-axis, 25.04, look in a little different area, 25.05, look in a little different area, 25.06, kind of come in differently, 25.06. And so again, I am just saying something that would be very, very accurate to say is about 0.05 millimeters. And so I'm seeing my behavior along the x-axis and the y-axis to be good to be within 0.05 millimeters. Now Z, I guess you didn't see that, 0.05 millimeters like that. Got to make sure I'm getting a good view. Okay, now let's come in for z-axis precision. And we did some of this, it's just we didn't write it down a couple of weeks ago, but now we're more formally writing it down. So we're going to come in and we're going to look along the z-axis. And in this case, what you can see is it's coming up a little bit smaller than I expected. It is coming up a little bit smaller than I expected. And it looks like about... and I'm just kind of eyeballing it. You could more formally average, okay? But as I go across here, I'm seeing overall that it is about 1/10. It is about 1/10 of a millimeter less than what I expected. So z-axis precision is 0.1 millimeter. And I don't think that's like plus or minus 0.1 millimeter. I think that the less than expected. And maybe up here I should put more than expected. So a lot of times in engineering, you see people put like plus or minus. I don't think this is a plus or minus number. I think the x-axis always is printing a little bit wide, and the y-axis is always printing a little bit wide. So I'm going to put here more than expected, because this will help me later when I'm designing things. Okay, now what is the minimum line width that we are going to be able to define? So that is down here. Okay, you see down here I printed a bunch of different lines, and I started here, and this was like 1.987654321, and then this was 1 millimeter, 0.9876543. Let me do it again. This is 1.9876, or this is 1.987654321, and then 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2. And so I can see a 0.2 millimeter line that I printed. And then right here where I'd said print a 0.1 millimeter line, it's not there. And so what is the minimum line width that I am able to print? Well, from this, I can see that I printed 0.2 millimeters. That is the minimum line that I was able to print. Now, it's kind of interesting if you think the nozzle is 0.4 millimeters and I'm printing at 0.2 millimeters, maybe that's kind of a rough rule of thumb that maybe you can kind of print to about half your nozzle width. But the other thing I'm also interested in is how well am I defining things? Like I told this one I wanted it to be 2 millimeters. And so let's come in and see what I actually got. And you can see that I wanted 2 and I got 2.01. So that's even better than what I was saying my, 2.01, 2.02. That's better than what my x-axis tolerance was. So if I said my x-axis tolerance is 0.05 millimeters, well, yeah, it's that or better. This one I wanted to be 1.9 and it's 1.9. 1.8. Okay, let's see if I can get that. 1.8. Do you see that? 1.68 where I wanted 1.7. Man, guys, this is just really amazing, the accuracy that I am getting on these things. What you also see is that it would be really great to come in here and label these things, emboss their size on here. So when you come back to this structure later, you're going to remember what it is. Okay, so this is 987654321, and then this would be 1.0. So let's come into this one, and let's see when I tried to print a millimeter line. Okay, I get about 1.05, so that is not terribly surprising. That's back to that kind of 0.05 millimeter precision. So let's say that was 1.0, this is 0.9, 0.8, 0.7, 0.6, 0.5. No, I think this is 0.2, 3, 4, 5. This would be 0.5 here, I think. And where I wanted 0.5, I'm getting 0.46. That's still within 0.05. And this would be 2, 3, 4. So this one we would expect to be 4, and that is what it is. And then we're going to come down to this amazing 0.2 millimeters. We wanted 0.2 millimeters, and we got 0.24. And so again, we're printing to 0.2 millimeters to within 0.05 millimeters. So that is really pretty amazing. Hopefully it makes sense what we're doing. We're just looking at our precision as a function of line width. And you can see that for different line widths, our precision is staying at 0.05 millimeters or better. Okay, now the corresponding things over here, I'm going to do those last. I'm going to come back and I am going to do those last. Now what I'm going to do is I'm going to look at my axle, my pin and hole connections. And remember, this one here was this was 15 millimeter peg and this was a 15 millimeter hole. And so this one would be 15.1, 2, 3, 4, 5. So if I come up to 15.5, it certainly fits in, but it is way looser than I would want. A 15 and a 15.4 is a little bit more snug. A 15.3, it's still very, very free to move around, very free to move around. Okay, not hanging. This one would be a 15 peg and a 15.2, a 15 peg and a 15.2. And I think I better check that design and make sure I'm remembering that right. So let's let's hop back over here. Let's look at my design. Let's I just want to make sure that I'm saying this right because we're going to write it down, right? And you're not seeing that, so I'll come over here. I'll turn the body off, and then I want to edit this sketch. Okay. Yeah, so this one is 15.1 and this one is 15.2. So it's going to be somewhere like at 15.2, it is completely free to move. At 15.2, it is completely free to move and there's no wobble. At 15.3, it fits a little bit nicer and there's no wobble, but I'm just afraid there might be a few high spots on there. And as you work this around, it's probably going to rub a little bit. And so I'm going to say that if I want a smooth fit of a wheel on an axle or a hole on a pin, I am going to want 0.2 millimeter tolerance. I'm going to want for this tolerance down here. .2 millimeters. And we did the minimum line width that we can do is 0.2 millimeters. And then we say that our cylindrical axle joint, we want a 2.2 millimeter tolerance. Okay. And let's see if we can understand that tolerance a little better. What I'm going to do is I'm going to come over here, and this was supposed to be 15 and it is round. And what it is coming in at is it is coming in at a little bit under that, 14.97. Okay, 14.97, 14.9. So you see it's coming in a little bit less than that. And then let's check the hole here. Okay, let's check the hole. And it is coming in even a little bit less than that. So you see, let me see if I can show you what I am doing here. This hole was supposed to be 15. And it is coming in at 14.8. All right, it's coming in at 14.8. So the hole is smaller than what we expected, and the pin is smaller than what we expected. But if we leave the hole, 0.2 millimeters more than the cylinder, it fits nicely. Okay, now let's see if we can get the tolerance for a snug fit. And that would be something that it would slip on and it would slip off, but it would hold snugly, like our eyeglass cases. What tolerance would we want there? Well, if I come up here to 15.1, that is too loose. You see, like if I just turn this over, that could fall off. But if I come over here to a 15 hole, and a 15 peg, that I would say is a tight fit. So what I would say is the tolerance for a snug fit would be 0 millimeters. And now for a compression fit, I got to be careful at doing this because I don't want it to really become a compression, because then I would lose this design. But clearly I can get that out. If I come here to 14.9, I think I could get it out. But I think here I can't get it in. So I think about 14.9 would be where I would get a compression fit. Tolerance for a compression fit, I would say, is minus 0.1 millimeters. So that would be peg is 0.1 larger than hole, like that. Okay. All right. Now let's come back up here and just see how precisely am I defining the peg precision? How precisely am I getting the diameter of the peg? We wanted this peg to be what? We wanted it to be 15. And what it is 14.9, 14.9, 14.9, 14.9. So this is 0.1 millimeter, and I'm going to be explicit here. Peg is smaller than expected. Okay, now let's look at the hole, and we are going to come over here. And remember, it was this hole that was supposed to be 15 millimeters. So we'll come in and we'll look at it. And what we can see is that the hole is about 14.6. The hole is about 14.6. Hole is H-O-L-E, not W-H-O-L-E. So this is 0.4 millimeters. Hole is smaller than expected. Okay, the hole is smaller than expected. And I'm gonna work with that a little bit more and see if that is really 0.4 is the number. So we'll come here. That's like 0.25. I'm just kind of trying to play around at looking at it at different places and different depths. So I'm finding probably, I'm going to say that I'm going to say after a few more measurements that the cylindrical hole precision is more like 0.3. Okay. And the hole is, I keep saying W, the hole is smaller than expected. Okay. And now this kind of makes sense. If the peg is 0.1 smaller than expected and the hole is 0.3 smaller than expected, then that kind of makes sense. That kind of makes sense of a 0.2 millimeter tolerance needed here, kind of like the difference between those two. And it sort of makes sense there, but just understand you're going to be off by a few tenths of a millimeter from what you expect when you're doing these things. Okay, so now what I want to do is I want to look into printing over air. And so remember, this was these structures where we made two columns. We made two columns, and then we tried to print between them over air. And we're going to see if I can zoom in here and look at what happened. Okay. I'll see if I can give you a view there. And I am really somewhat amazed at how this was able to print this far over air with these undersides still looking really good. And so how far did we print there? So you see, really, I would want to redesign this on my next iteration. I would want to have more of a range bigger than this so that we finally get a gap to where this thing fails. But it looks like that I can print over an air gap of what? I can print over an air gap of, it looks like 23 millimeters. 23 millimeters. I can print over an air gap of 23 millimeters. And I am going to say that I am really quite surprised at that. 23 millimeters. So you can kind of define a flat area over air, a pretty long region. Now, I probably should say that that's when you are bridging between two solid objects, that if I'd made this a diving board, I would doubt that I could get something out that far. So maybe it would be good for us to create another set, over here that were diving board structures to try to kind of understand that particular, parameter. Guys, does this make sense, or is this just totally, completely, utterly boring you? Or are you understanding that what we are doing is we're getting a feel for what we can expect to get out of our printer? Now, for the thing that we haven't done yet is the minimum spacings that we can define. So if you look here, I started by creating a 2 millimeter gap. That looks great. A 1.9, 1.8, 1.7, 1.6, smaller and smaller and smaller gaps. So let's just start here and look and see how precisely did we get this gap that we wanted to be that we wanted to be 2 millimeters. And I can come in, and this is actually kind of a hard measurement to make. And you can see 2.06, again, that theme that we're seeing of a precision in the X and Y axis of about 0.05 millimeters. And so I'm not going to measure each one of these. You can look at it. But what I'm going to do is I'm going to come in and I'm going to look. And I am actually somewhat surprised in that I am clearly getting a 0.2 millimeter gap here. I am very clearly seeing a 0.2 millimeter gap. And let's see if we can zoom in for you guys there. Okay. Can you see here on this one that that's clearly a 0.2 millimeter gap? And in fact, I could probably slip a piece of paper down in there. Yeah, you see I've got a piece of paper that I can slip in that gap, so I know that that gap is really there. And as I look at it, I'm not seeing any bridging. Now, the interesting thing is, which is even maybe more of a surprise to me, I am seeing that it is really close to getting a 1/10 of a millimeter gap, but I am seeing bridging here on the corner. And then you can see the bridging almost happened here on the corner, but the gap is still open. So let me go ahead and capture that the minimum space that I can define is 0.2 millimeters. That's the minimum gap that I can define. But wow, I almost got a 0.1 millimeter gap. All right, so today's topic is about metrology. What is your most important metrology tool? Your calipers. that is what you need. That is what hopefully you guys have. This is something that we're going to be using for the rest of the lessons in these Fusion 360 lessons. But guys, there's another metrology tool that I'm going to show you, and you don't have to order this. It's just, if you can, it is a pretty neat little thing, and it is a USB microscope. I ordered about 5 or 6 of these. This is the best one that I found out of the 5 or 6 that I ordered. If you want this, it will help you do up-close inspections of your 3D prints. You don't have to have it. If it's out of your budget, I think it's about $70 or something like that. Just watch me do it. Don't worry, you don't need this to complete the class. But I'll just kind of show you the capabilities. I was pretty blown away by what this little handheld microscope could do. So I'm going to come down here. You know, guys, every day you see those ants on my breadboard, and so I'm going to come in here over this ant. Let's see if I can find him. This is one of those little tiny sugar ants or builder ants. And the absolutely amazing thing to me is that we're actually able to go in and see the facets on his eye. Or if we look out on that antenna, we can see even down to the hairs on the antenna. We're getting definition on. And you can see those mandibles that he's got there, the little hairs on his face. And so this is a pretty incredible little handheld microscope. And I'm just showing you this because it shows you the precision that you can get with this little microscope. But what are we going to do today? We're going to be looking at this 0.1 millimeter gap that we were trying to get. And I'll show you something kind of neat. This has 2 focal points, one a lower magnification focal point and one a higher magnification focal point. Let me just show you that on the ant. So I can come down here and I can focus on the ant with low magnification, or I can come up here and it will focus on higher magnification. So with one lens, there's 2 different points of focus, a high magnification and a low magnification. Let's go back to the low magnification. Okay, and now let's come in and let's look at this, this line that we had defined. And so this is the 0.2 millimeter line. And so let's look at that, the 0.2 millimeter line. It's the dark orange. And if you look down here, you can see at the corners, there still is an open gap, but it is closed up. The gap isn't. The gap is no longer 0.2 millimeters. It looks like the gap is coming down to about 0.1 millimeters. So my gap is choking off at the corners. And so this is kind of cool. Look how nicely and precisely that 0.2 millimeter gap is being defined. It is super clean. But then we start having a little confusion at the corners. And if we come here at 0.3, same type of thing. You see how it's bulging at the corners? And even if we go all the way out here to our 2 millimeter gap, it is bulging at the corners. Now, when you've got a nice big gap, you don't care that it's bulging at the corners, but you can see that that is where the problem is. And so let's come back here. This is our 0.2. Let me see if I can switch over to the high magnification. Okay, there is our high magnification. And come down, and you can see definitely I'm having a problem at the corners. Now let's go to the 0.1 millimeter gap, and you can see at the 0.1 millimeters, I'm actually getting bridging occurring at the corners. And you could kind of think that if I'm bulging 0.1 millimeters at the corner and I have a 0.1 millimeter gap, then I am closing that gap on the corner. The other thing that I really like about this little microscope It comes with a little measurement gauge. And let me show you what is really, really super neat. You could imagine that little gap that I just made is very hard. That little gap that I just made would be very hard to get the calipers and do any type of metrology on. But what I want you to see is this has like a little clear ruler, and each one of these little things is 1 millimeter. So you can see that I can put this clear ruler over. And so let's say that I come over here to here. And let me go down to my lower. Okay, let me see if I can get some focus here. It's like I need one more hand to really do this well. I'm not. Okay, let me see if I can look at this. I'm having trouble seeing. Okay, so it's 0.5. So every 2 marks is 1/10 of a millimeter. Every 2 marks is 1/10 of a millimeter. Okay. Okay. So every mark is 1/4 millimeter. So you can see it's 0.25 every mark is 1/2 of a millimeter. I said it right now. Every mark is 1/2 of a millimeter. So I go 0.5, 1, 1.5, 2. So you can see that we are measuring 2 millimeters there where we expect 2 millimeters. But now what it also has is you're going to get so small that you can't measure that way. And what it has is it has lines. This line, that line is 0.076 millimeters. This line, the width of that line is 0.1 millimeters. So let's get that 0.1 millimeter down here. Let's see if I can get this down here. Okay, that's 0.4, 0.3, 0.2, and this is 0.1. And then I'm going to put that 0.1 gauge. I've got that 0.1 gauge right over my 0.1 gap. And I can see it, but now I got to get it where you can see it. Okay, so can you see that that 0.1 millimeter line is just absolutely perfectly reflecting my 0.1 millimeter gap? And so this, I know it's tedious, you guys trying to watch me get this lined up, but you see what my gauge says is 0.1 millimeter is kind of like exactly the gap that I'm getting. So I am precisely defining a 0.1 millimeter gap as I wanted to, but then the problem comes down here in the corners where I get the bridging. Now let's go back over here and let's look at that line that we tried to make at 0.2 millimeters. Okay, this was 0.2 millimeter line here. And so that's 0.5, 0.3, 0.2. Okay, so you see the orange is what I printed. and then the black is my gauge. And you can see an amazing precision with which we were able to print a 0.2 millimeter line. So that is absolutely amazing. So guys, the thing that I love about this camera is it came with this little gauge that allows me to start getting precision down in the very, very, very detailed work, the very, very detailed work that would be hard for us to do using the vernier calipers. So let's come back over here. Let me scoot back out. Let's put this back up here. Let's put this back up here. And let's put this back up here. Okay. I fear that this has been very tedious and I have just bored you guys. But let me just tell you that this is such an important design concept, which is designing to the manufacturing capability that you are going to be building in. We are doing this with a 3D printer. We are now understanding what the print capability of our printer is. And that is just going to be really, really, really important moving forward. So what I am doing is I am putting this and this and this, and I am putting my calipers beside my printer and in front of my Fusion 360 design workstation. And as I am working in Fusion 360 moving forward, I am always going to have this in front of me, reminding me, and also having this in front of me to remind me to be designing to the precision and capability of my 3D printer. Wow, I've done a lot of talking, and I hope that this lesson didn't make you guys weary. What I will say is that, man, if there was one thing, okay, I'm not going to do this because I know that this is like the third lesson on design rules, and I know that you guys would finally just go away and start watching silly cat videos or something like that. But I got to show you one more thing. And I used to do this when we were designing integrated circuits. We had a problem just like this. And so just give me a second to digress. Just give me a second to digress, because when I see this, I have seen this problem before. Okay. And so what you see here is I'm going back to this one is right here. This one is the 0.1 millimeter. This one is the 0.1 millimeter. This one is the 0.1 millimeter space. And look how beautiful that 0.1 millimeter space is until we get to the corner. And then look how ugly it gets at the corner, right? So what I would dearly love to do, and I'm probably going to do it, but I'm probably just not going to make a lesson on it because it would bore you guys too much. But what would you do here? Okay, if your corners are bulging out, maybe if we are going to do precision design work and we really needed like 1/10 of a millimeter gap, if we really needed 1/10 of a millimeter gap, what would we maybe do? Maybe we wouldn't make the corner square in Fusion 360. Maybe we would put features on our corners such that when we print them, we end up not with what we drew, but with square corners. And that could almost be a design challenge if some of you guys are really interested in this type of stuff, to go in and to see who could design the most square corners by creating an optimum shape that keeps our corners from blowing out. Okay, guys, I appreciate your patience with me. And I hope that I haven't just absolutely bored you guys to death with these three lessons on design rules. I promise you that next week we're going to be going back to designing things that are fun, designing things that are useful, printing them out, continuing to build our design skills, then continuing to build our print skills. I think that we'll probably spend a couple of more lessons just getting more skill in Fusion 360. And then I think what I'll do is I'll probably come back and then start talking about upgrades for the printers. We'll start talking about getting more performance out of the printer. We can kind of see what we can do now with our printer, and then we're going to start working on getting more performance out of our printer by upgrading it. And I'll be showing you the biggest bang for your buck, how you can spend the smallest number of dollars and get the greatest increase in performance out of your printer. And I'll say there's things that are going to cost $5 or $6 or $7 that are really going to allow us to get better performance out of this printer. Okay, guys. I really hope you're having as much fun taking these lessons as I am making them. If you enjoy them, be sure to give us a thumbs up. That helps us with YouTube. Also, leave a comment down below. That will show YouTube that there's interest in these videos. Subscribe to the channel. And then most importantly, find someone to share these with. You know, if YouTube is not showing us a lot of love and offering these videos to people, share them with people that you know in your community, family members. And that's important because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.